All right, diving in today, folks, with a real head-scratcher. One of you brilliant listeners wrote in asking, how on earth can we tell the difference between a black hole and a wormhole? I mean, they both come from Einstein's theory of relativity, right? And they're both, well, pretty extreme objects.
Right.
Could even look similar from afar.
Yeah.
But the sources you send in point to some really cool ways we might actually be able to tell them apart. So that's what we're going to dive into today.
Yeah, absolutely. And we're going to have to get into some pretty hypothetical territory here. We're talking about wormholes, which are, well, as you said, theoretical tunnels that could connect different universes or even distant points in our own universe.
Right. Shortcuts through space-time. Pretty wild stuff.
Wild is an understatement.
So before we get too far, I think it's worth clarifying what kind of wormhole we're talking about here, because there are a lot of different ideas about what a wormhole could be like.
Absolutely. For this deep dive, we're going to focus on a traversable wormhole. So imagine a wormhole you could actually travel through, kept open by something called exotic matter. We'll talk about that a bit more later, but basically it has some pretty unusual properties that could make this whole thing possible.
Okay, so traversable wormhole. Got it. Now, the million-dollar question.
Yeah.
What's the fundamental difference that could allow us to say, hey, that's a wormhole over there, not a black hole?
Well, the sources you provided suggest that the key difference is all about connectivity. You see, a black hole, that's a cosmic dead end. Anything that crosses its event horizon, that's the point of no return, is trapped forever. But a wormhole, it could act like a bridge between two different regions of space-time. In theory, you could travel through it, and it could allow gravitational influences to pass from one side to the other. Imagine two bowls of water connected by a thin tube. Any ripples or disturbances in one bowl, they could travel through that tube and affect the water in the other bowl.
Okay, yeah, that's a great analogy. I'm starting to get the picture. So how would we actually look for these ripples between space-times? The sources you sent mentioned something about observing stars.
Exactly. The big idea here is that if we could detect the subtle gravitational effects of objects on the other side of a wormhole, that would be a smoking gun. Because unlike a black hole, which isolates its own space-time, a wormhole could allow the gravity of objects on one side to influence the stars on the other.
Okay, I'm following. So let's say we're observing a star orbiting something massive. What would the baseline behavior look like? I mean, if it was just a black hole or a wormhole in isolation, what would we expect to see?
Right, so to understand the difference, we need to start with that baseline. Your sources use a pretty standard model for spacetime, one that starts out flat, like regular empty space, far away from the object. The key is whether the star is orbiting a black hole or a wormhole with the same gravitational pull, its motion would look the same. And the way its light gets stretched or squeezed, the redshift or blue shift, that would be identical too. We wouldn't be able to tell them apart just by looking at the light from that star.
Okay, so redshift or blue shift alone, not enough. Gotcha. So how do we introduce the potential difference? You mentioned something about a test space-time and gravitational wobbles, right?
Right. Imagine a really massive star orbiting the wormhole on the other side in this test space-time. Now, the star is big, it's got a lot of gravity, and it's going to be creating these ripples in space-time as it orbits.
Like a cosmic speedboat, just creating waves as it goes.
Yeah, something like that. And here's the mind-bending part. Your sources suggest that these ripples, these gravitational waves, could travel through the wormhole and affect this space-time on our side, the reception space-time.
Oh, okay, so like a gravitational echo from the other side. So how do scientists model and analyze these echoes? The paper you sent, it mentioned some pretty intense math.
Yeah, it gets pretty complex. Scientists use these mathematical tools called gauge invariant perturbations. It's basically a way to make sure they're looking at real changes in the fabric of space-time caused by these ripples, not just some mathematical artifacts.
So cutting through the jargon, they're basically analyzing how the gravity from that distant star on the other side of the wormhole is warping space-time on our side.
Precisely. And to simplify things, they often assume that this distant star is in a nice, stable, circular orbit around the wormhole. It just makes the calculations a bit easier.
Makes sense. So these gravitational ripples arrive on our side. Now what should we look for in the stars orbiting the wormhole on our side? How would their orbits or their light change compared to if they were orbiting just a plain old black hole?
Well, those incoming gravitational ripples, they can actually slightly change the paths of the stars orbiting the wormhole on our side. It wouldn't be a huge effect, but it would change their kinematic shifts, those red shifts and blue shifts we talked about earlier.
Got it. So a tiny wobble in the star's motion.
Yeah. And what's really interesting is that your sources indicate this gravitational influence would make the star's orbit a little less wobbly, less erratic. Technically, they say it suppresses the precession of the star's orbit.
Less wobbly orbits. Fascinating. And what about the light coming from those stars? Would that change too?
Yes, that's the key, actually. The sources predict a decrease in those photon frequency shifts, the Eskin, because of the gravitational ripples coming from the other side. So a red shift might become a tiny bit less red, a blue shift a tiny bit less blue, compared to what we'd expect if it were orbiting a black hole with the same mass.
So these subtle changes in the color of the starlight, these tiny differences in redshift and blue shift, that's how we could potentially tell a wormhole from a black hole.
Exactly. If we can build telescopes sensitive enough to measure these incredibly small variations in the frequencies of light coming from distant stars, it could be our first real way to confirm the existence of wormholes.
That is mind-blowing. So to recap, wormholes, unlike black holes, could create this kind of gravitational link between different parts of the universe. And we might be able to detect that link by carefully measuring these tiny shifts in the light coming from stars orbiting the wormhole on our side.
Yeah, that's it in a nutshell. It gives us a way to test a concept that seemed, purely theoretical not too long ago.
But I gotta say, this sounds like searching for a needle in a cosmic haystack. These effects, they must be incredibly small.
Oh, they are. We're talking tiny, tiny variations. It would take incredibly advanced telescopes and huge comprehensive sky surveys to even have a chance of detecting them.
Well, fingers crossed we get there someday. You know, this really makes you think about the universe in a whole new way, doesn't it?
Yeah.
This idea that seemingly isolated events happening billions of light years away could have these subtle, rippling effects across the cosmos.
It really does. And who knows what other mind-bending discoveries might be out there just waiting for us to find them.
It's a pretty exciting time to be studying the universe, that's for sure. Great deep dive today. Really appreciate you helping us unpack all of this.
My pleasure. Always happy to talk about this stuff.
And for all you listeners out there, keep those questions coming. Who knows what mind-bending mysteries will unravel next time? Until then, happy stargazing.
Bye, everyone.